Hello, everyone. Wish you a good morning, good afternoon, good evening, depending on where you are. My name is Ronak Shah. I'm a product marketing manager at Ansys. On behalf of Ansys, I'd like to welcome you to today's session titled Ansys Solutions for Electric Machines and Drives. We are joined today by Pavni Gotipati. She has a PhD in electrical and computer engineering with a focus on electric machines, specifically permanent magnet synchronous machines. She has been with Ansys from 9+ years now and works as an application engineering manager for the low frequency team at Ansys. All right. So, Pavni, like the first thing that we want to talk about in this session, and everyone is always curious about when they hear about simulation software and how it's helping, is about customers. So let's talk about customers first and their real life products. How is Ansys Maxwell, that is our low frequency solution from Ansys, helping customers realize their product potential? If we can start with some examples of real life products, that will be a great start to the session.
Thank you, Ronak. That's a great start to this presentation. And here I have a few customer stories that I would like to share with our attendees. So the first and foremost being, as you might have guessed from this short video here, is Lucid Motors. And I would like to talk about how Lucid Motors has been using Maxwell and Ansys solutions successfully in their product design. First and foremost, just a quick introduction to Lucid Motors. As we all know, Lucid Motors is an automotive company with headquarters based in Silicon Valley and a manufacturing facility in Arizona. Their focus is on creating a high-performing, most efficient electric car. The center of this electric drivetrain ecosystem is an electric motor. These motors can spin up to 20,000 RPM, should be volumetrically compact, reduce electrical losses, and maximize power output. The motor also features an innovative cooling system that more effectively removes heat from the stator winding, minimizing losses and boosting efficiency. And as we see on this slide here, currently Lucid Motor has been using Ansys Maxwell to simulate the losses in electric machine. Specifically on this one here, it's an induction motor. And we can couple these losses from Maxwell into Ansys Fluent. So in Fluent, we can investigate the e-motor thermal management by solving a conjugate heat transfer model. Since the motor is cooled by an oil spray, as we can see in the middle section of this slide, we simulate the oil flow by a transient two-phase flow model and find oil distribution and splashing as shown in the animation here. We also find how much heat is extracted by spray oil cooling. This motor has also a water jacket for stator cooling. We solve heat transfer in solid components and water jacket and obtain temperature distribution as shown here on the right. In the CHT model, heat losses from Maxwell are mapped using Maxwell fluent coupling, and heat extracted by oil cooling is accounted for by applying heat transfer coefficients from the model. And continuing the study, not only we can do Maxwell Fluent for thermal coupling, but we can also take the temperature distribution from Fluent and couple with Ansys Mechanical structural solver to see how this temperature affects the principal stress of the motor. Further, we can take this structural solution, couple it with ENCODE, and see how many cycles it takes to failure or analyze the life of this product. The second story that I have today for our attendees is from WEG, which is a global electric component company. WEG is a multinational company that produces electric motors, generators, transformers, drives, among other things. It is a global motor manufacturer that designs motors for many applications, ranging from electrical propulsion systems for aircraft to large 4-megawatt wind turbines. Its focus is on producing highly efficient motors with extra long life and energy savings. The problem that we are showing here is a large induction machine and is extremely difficult to solve in time domain because both rotor and stator, made of highly nonlinear electrical steel, were designed with very complex geometries, including skewed rotor bars with large induced eddy currents. The total number of time steps required to achieve an accurate solution at steady state conditions made this entire case study prohibitive using traditional time stepping simulations, as shown here as non-TDM, which takes a long time to solve. And using our high performance computing solution, and again with time decomposition method, WEG was able to reduce the total computation time by a factor of 70 times, from almost 50 days without using HPC and with a non-TDM solution to less than a day or less than even quarter a day. The main contributor to overall HPC performance is the number of parallel MPI processes deployed. So as we can see, as we increase the number of tasks and the total number of cores, the simulation time reduces significantly. This TDM provided not only a very fast transient solution of dynamic performance of motor design, but is also reduced the total decision time with multiple design points. So this makes Ansys Maxwell transient solutions suitable for robust design and optimization. The third story that I have today for our attendees is from Schaeffler Group. Schaeffler is a German manufacturer of high precision components and of rolling element bearings for automotive, aerospace, and industrial uses. One of these focus areas for Schaeffler include designing powertrains for electric and hybrid cars. As we see in this study here, Schaeffler is successfully able to use Ansys motorcad with OptiSlang for duty cycle based optimization methodology that will help product designers identify the relationships between the e-machine's behavior and specific geometrical parameters under real world conditions. This will help to minimize winding and core losses during specific drive cycles. Schaeffler is not only able to achieve a accuracy of over 95% for these simulations, but was also able to run these design iterations more rapidly, reducing the simulation time. This computationally efficient workflow enables multi-physics and multi-objective design optimization of the electric machine. And finally, Schaeffler was able to see the cost reduction by optimizing the magnet volume when doing this study by coupling motorcad with Ansys OptiSlang.
Thanks, Pavni. These were great customer applications and very complex designs that we covered. But sometimes what we notice in the industry is that companies even lack the expertise in electromagnetics. I'm curious to understand, how is Schaeffler able to explore these motor designs so quickly? It would surely be requiring a team of very efficient and experienced engineers, isn't it?
That's a great question, Ronak, and how Schaeffler is able to achieve this. And you're right. Electric machine design is a complex subject and often requires expertise. But the beauty with this solution, what MotorCAD offers, and I would go through in a few slides, and how MotorCAD makes it easy for product designers to easily analyze the electric machines. So to start with, I would like to first address the challenges for electric machine design. And these challenges have been evolving over the decade. So maybe if you recall, about 10 years ago, most of the electric machine design was centered around single physics, fixed operating conditions, and most electrical engineers would be just looking at as an electromagnetic problem. And and over the last decade, the evolution has been that, electromagnetic, the machines the electromagnetic performance itself is not only a indicator of the machine performance, but we need to account for multiple physics. In electric machines, we have windings, which means that we have winding losses, AC losses. We have stator and rotor, which means that there are core losses now. And anytime we have losses, that means we will have a thermal impact. So we need a thermal solution. And not only that, due to the tangential and radial forces in machines, we can have deformation effects on the stator teeth, for example, and that would mean a structural issue. So with this kind of electric machines, it really is a multi-physics problem and we need to account for wide torque and speed operating range. It would also command a rapid development cycle, especially if you are in the initial design stage of an electric machine where you are trying to see how many poles should I use? How many slots should I use? Should I use N42 versus N52 material, or a different magnet material or a different stator material? So there are a lot of what if questions, and these can be addressed quickly using motorcad for that initial design stage. So with motorcad, we can provide that rapid multi-physics design solution, and also couple that solution with more specialist physics-based numerical tools for multi-physics analysis. And how this would translate is through our partnership with motorcad and Ansys. We can build an end-to-end workflow for electric machine design, Motor Design Limited or motorcad for initial design, and for fast multi-physics design of electric machines, and Ansys tools, including Maxwell and Fluent or Mechanical, for a more detailed multi-physics prototyping and efficiency of the machines all along the life cycle. So with this solution, we have a complete solution for the initial sizing decisions, initial design decisions, to a more detailed validation stage. And what does motorcad provide? So motorcad is a market-leading tool dedicated to the design and analysis of electric motors. Motorcad has 4 modules: EMAG, thermal, mechanical, and lab modules that provide solutions in each physics area. For example, the electromagnetic module or EMAG module calculates torque, power, losses, voltages, currents, inductances, flux linkages, forces, and any electromagnetic solution. The designs can be input and calculated in minutes, allowing lots of iterations quickly. The thermal module can calculate temperature of motor components in steady state and transient operating conditions. It enables the user to understand main heat transfer paths and opportunities to significantly improve output. It can also generate a thermal and flow network automatically. It can do 3D network. The 3D network it generates includes radial and axial heat transfer. The mechanical module in motorcad can provide some solutions for stress and displacement in rotors during operation. And the lab module is a virtual testing laboratory that can calculate efficiency and loss maps, torque speed curves, perform duty cycle analysis, and provide the operation of the motor over a wide range of operating conditions. So this tool is also has embedded engineering expertise that makes it quick and easily, quickly iterative mode evaluate, that makes it easy to quickly and iteratively evaluate motor topologies. And many new and enhanced features in the latest releases of motorcad includes ratio-based geometry templates, where the user can easily specify the ratios for the geometry to enable optimization. It does include system-level simulation capabilities, where multi-physics motor models can be included at system-level simulations for highly accurate and fast solution times. And it also automates the export into Ansys Maxwell and 2D and 3D for a more detailed FEA analysis. This includes options to export custom CAD geometries, hairpin windings, and axial skewing and segmentation. So the user can take their motorcad models and do a more detailed physics analysis with Ansys Maxwell and Fluent or Mechanical.
Thank you, Pavni. So from what you said, it seems like motor designers can consider even the multi-physics capability into the initial design of machine using ANSYS MotorCAD. But this was about initial machine design. How can the engineers account for the important manufacturing or even advanced effects like hysteresis in the electromagnetic simulation of electric machines?
We can definitely consider manufacturing effects and advanced electromagnetic effects in the simulation by coupling motorcad with Ansys Maxwell. And just to cover some of those detailed effects, one of the main modeling would be the loss modeling in electric machines. And with losses, we can categorize the losses into two types of losses. Core losses is one type, and the second one would be the ohmic loss. So with core losses, Maxwell can model detailed core loss either using Steinmetz model, hysteresis model, or anisotropic nonlinear core loss model. And while computing the core loss, Maxwell also can consider the normal flux to laminations and include that effect in the loss computation as well. So some of the core loss capabilities included in Maxwell would be ability to compute core loss versus frequency and how the temperature would affect the core loss. We can also see the core loss effect on field. And there is also an option to customize the core loss model based on the user needs. The second loss category here would be the ohmic loss calculation. With Maxwell, we can compute ohmic losses, be it the induced eddy current losses in permanent magnets. It may be the rotor bars or stator bar windings, and accounting for the induced eddy losses in the rotor and stator bars as well, or even accounting for temperature dependent conductivity. And what if the customer has a leads wire for their winding? So in the latest releases for Maxwell, we can also account for leads wire effects without having to explicitly model the leads bundle. And I'll go into more detail on each one of these. So about the leads wire modeling, in the latest releases of Maxwell, there is a new algorithm built into Maxwell that can account for leads winding losses and impedances. So when defining the material in Maxwell, the user has the option to specify the wire composition is leads, and they can specify if it is a round wire, square wire, rectangular wire, then specify the strand number and the wire diameter, and account for additional ohmic loss due to skin and proximity effects in the solution. It could also compute the stranded loss AC as well as the AC impedance matrix with the leads wire in the latest release. As an example here, we can see the effect of leads wires in the loss computation. And when the traditional approach for leads wire modeling would include modeling each strand of the leads bundle explicitly in the geometry, and using this new approach of leads wire composition in the material properties, we can just model a lumped copper conductor here and still emulate the ohmic loss accurately with this new approach. So the advantage with this approach is obviously the reduced simulation time, reduced complexity of the model, but not compromising on the accuracy, while we are getting the same accurate solution with this leads bundle. The second type of loss here is again core loss calculation. We can account for anisotropic core loss or temperature dependent core loss in Maxwell. With anisotropic core loss, we can specify the different core loss coefficients in the three different principal directions. So we can take the data from the manufacturer data sheet and we can plug that into Maxwell and specify different core loss coefficients in each of the principal directions. We can also account for temperature dependent core loss. So the users can specify a third type of core loss model, which is the BP curve in the material properties. With that, the user can specify different core loss curves at different temperatures. And Maxwell can then extract the Steinmetz core loss coefficients at each temperature and use that for providing the spatial core loss distribution. So here we can account for a core loss that varies with both magnetic flux and temperature. We can also account for manufacturing effects in core loss computation. So when defining the core loss, the user can input the core loss curves and the Maxwell can compute the equivalent cut depth. It is used to construct the regression curves versus input curves, and it is also used to account for the core loss manufacturing effects in the solution. Another advanced capability with Maxwell is the vector hysteresis modeling. We can use Maxwell to regenerate the major loops or even the minor loops. So with major loop formulation, it is suitable for studying the hysteresis behavior, but not the losses. And it is faster than the minor loop formulation. Whereas minor loop formulation can accurately generate the minor loops with the vector hysteresis model, and it can use these loops to compute the hysteresis loss as well. We can also specify temperature dependent BH curves in the material properties. So as you can see here, for example, for a rotor or stator made of carbon steel, I can specify the BH curves at different temperatures. And solver will then interpolate to recreate new nonlinear BH curves based on the specified computed temperature element by element. And this is also this will also support two-way thermal coupling. And with this approach, we can see how the induced voltage, for example, here varies at different temperatures. In a similar way, we can see how the torque would be dependent on the temperature. And more on that here in the next section, where we can talk about demagnetization. And this demagnetization one could be temperature dependent. And what I'm going to cover on this slide here is based on the short circuit demagnetization model. So let's say we have a permanent magnet motor, an IPM motor as shown in the screenshot, and the permanent magnet is defined with a BH curve. And the stator winding, for example, here is specified for a short circuit condition. We can provide arbitrary current or voltage versus time profile for the stator windings. And if we take an operating point inside the magnet, we can see how this the BH field is tracked at the top out at that specific point. So we can see that the field increases. And basically due to the demagnetization, as the current is changing in the stator winding, it can the operating point can track a recoil line here. And that can basically, when it drops below the knee, that may lead to demagnetization. And as we can see here, when it is in the linear portion, when it is above the knee, the flux density distribution in the magnet, and when it falls below the knee, we can see the demagnetization effect in the flux density distribution here. The second demagnetization effect could be temperature, due to temperature dependency of permanent magnets. And if we take a typical manufacturer data sheet, we can see the BH curves of permanent magnet changes with the temperature. And now in Maxwell, we can basically specify thermal modifiers for permanent magnets as well. And we can see how the torque performance or the flux density in the magnet would change with temperature. So this can be done inside Maxwell, or this can also be done by coupling with a thermal solver like Ansys Fluent or Mechanical and feeding the temperature back from the thermal tool back into Maxwell. As we can see here, at room temperature, the flux density is much higher compared to a temperature of 110 Celsius, where the magnet may be irreversibly demagnetized, in which case it is fatal for the machine performance. Another advanced effect that we can model with Maxwell, and again coupling with some of our mechanical tools here, is magnetostriction. Magnetostriction is a property of ferromagnetic materials that causes their deformation during the process of magnetization. For example, we can take that the structure of such materials is divided into domains, each of which is a region of uniform magnetic polarization. When a magnetic field is applied to this domain, the domains rotate, causing a change in material's dimensions. This change in material's dimension is due to anisotropic crystalline structure of the material. And now with Maxwell, we can account for this magnetostriction effects in the electromagnetic performance. So in the material properties, the user can specify the stress strain curves in the material properties. The user can also compute inverse magnetostrictive effect and specify the curves for the inverse magnetostriction as well. Maxwell will compute the electromagnetic forces together with the magnetostrictive forces, and we can see the magnetostrictive forces and the electromagnetic force both in the radial direction and the tangential direction. So we can compute the total radial and tangential forces on the tooth tips. And we can see how that magnetostrictive force will influence the surface force density on the tooth tips. So here on in this picture, we can see the surface force density without magnetostriction modeling and with magnetostriction modeling.
Thank you for that answer, Pavni. So you just mentioned mechanical. Are you talking about coupling between an electromagnetic and a mechanical solution? How can we account for multiphysics effects in the electric machine simulations?
That's a great question, Ronak. So multiphysics is a key aspect for electric machine design, and detecting any issues, for example, related to acoustics and noise vibration issues with electric machines would save the customers a lot of redesigning at a later stage when they detect these issues early on in the simulation. So typically when an electrical engineer designs a machine, noise is not one of the top things on their mind. As an electrical engineer, I would be looking for high torque density, high efficiency, but noise would be the last in my list. So accounting for the NVH issues early on in the simulation would reduce any potential issues later on in the design cycle when I go to test my motor on the dyne and, oh, it sounds too loud, and it's too late to make any design changes at that point. So accounting for this in simulation will help us to identify these issues. And how simulation can be used is we can not only account for the noise and vibration originated from electric machines, but we can also identify and model any other contributing noise sources, such as any structural borne noise or vibroacoustics and things like that. So we can account for all three types of noise sources: electromagnetic, mechanical, and airflow noise sources. And on this presentation, we will focus on the electromagnetic noise generation, which is typically from the electric machine. We can efficiently and accurately predict the electromagnetic forces, the gap forces, the radiant and tangential forces on the teeth. And we can take this into a mechanical solver to identify how we can optimize the NVH profile for the machine. And to go into the details of this workflow, we can start with an electromagnetic simulation like Maxwell, where we define the stator excitations and we can extract the forces on the stator tooth tips. And we can then couple with mechanical, any structural borne noise, and combine the electromagnetic noise with the structural borne noise to see how does the full noise profile look like. We can even take that into our VR experience tool to even understand the sound perception and audibly hear the noise as well. And the tools that would facilitate this workflow is, as we can see here, we can start with just structural noise, again, in mechanical. We can do structural pretension analysis, modal analysis in mechanical. We can use Maxwell to compute the electromagnetic noise. We can combine these two, the mechanical noise as well as electromagnetic forces from Maxwell, in the harmonic response solver in mechanical, and do a harmonic acoustic analysis. So we can generate a waterfall diagram that will help us understand the noise at different acoustic frequencies and different speeds of operation of the electric machine. And we can also extend this workflow with Ansys Motion. Ansys Motion is an RBD solver with flexible structural capabilities. Motion has both frequency domain and transient domain solvers for gearbox and drivetrain simulation. Users can map electromagnetic forces calculated from Ansys Maxwell to the finite element structural model of Ansys Motion. This method uses time domain Maxwell to time domain motion mapping, so there is no FFT required in this process. The map DM forces drives and excites the entire e-powertrain. So in this powertrain, there is excitation coming from the electric machine and from the gear train, as we can see in this picture here. Electric machine forces, which are usually a combination of torque fluctuation and radial excitation, are applied to the teeth of the stator, can be calculated using Ansys Maxwell. The vibration and excitation from gear is called transmission error, We can calculate the transmission error based on the applied torque. The misalignment of the gears and the contact behavior between the gear teeth can thus be modeled with motion, and we can look at the total housing vibration response using this workflow. And we can go one step further by taking the motion data into Ansys Vr Experience. So with the Vr Experience, we don't have to create acoustic mesh to calculate sound pressure because it is using boundary elements. In this case, it is the Rayleigh method. So the sound pressure calculation based on the surface velocity of the FE of the finite element bodies can be calculated and we can look at the sound pressure at any microphone points. And with this, we can even listen to the audible noise in the VR Experience tool. And I can actually play how this structure would sound like in this animation. Just give me one moment. So if you can hear that, that is basically the how the noise would sound like from this unit.
All right, so we have multiphysics capability that is required and evident. Do these multiphysics analysis require designer to define the right materials? Do we have anything to address that, Pavni?
That's a great question, Ronak. One of the challenging areas for electric machine designers or for any finite element modeling is the material definition. And getting the material definition can be cumbersome. It would need the users to check with their vendor to get the material properties, and these material properties need to account for the appropriate physics. So if I would be defining the materials in Maxwell, I would be looking at the electromagnetic properties of the materials like conductivity, permeability. But if I would be using the material in a structural domain, I would be looking at structural parameters of that material. So acquiring these material properties for different physics analysis can be cumbersome. And with Granta materials data for simulation, we can address that challenge easily. Granta materials data for simulation includes several vendor libraries, and in the most latest release, we can see here for Maxwell, there are 93 producers. Libraries included with a total of 1936 materials, almost 2000 materials included. And some of these materials, as you can see, includes hard magnets such as permanent magnet material definitions. You can see vendor libraries like ordinal magnetics, vacuum schmelz, Shinetsu, and several other permanent magnet libraries, but also you can see some soft steel materials like Carpenter Technologies and other soft steel libraries. So it is very likely that as a user, they can find a material that they would need from this extensive library. And the beauty with Granta is that these materials include all the material definitions for different physics. So a Maxwell user can also go into mechanical, or the mechanical user can find the appropriate mechanical properties inside mechanical from these producers. So it's easy to do multi-physics analysis by providing such capability with the Granta materials data for simulation.
So, Pavni, great to know the capability we have for materials across different physics at ANSYS. How can someone optimize motors not just electromagnetically, but also for thermal and structural performance?
Great question, Ronak. So optimization is a key part of electric machine design. So a typical design process for electric machine would involve an initial design stage where you're trying to see how many poles, how many slots or what material to use. But also a more detailed design for electric machine would involve optimizing parameters such as the magnet thickness. Everybody would want to reduce the magnet volume to cut down the cost of the machine. So users would want to optimize the magnet sizing, and other parameters like the slot height, slot opening width, and things like that. So that detailed design can be done together with Maxwell and OptiSlang. So in Maxwell, we can identify the parameters that we want to include in an optimization study, and we can plug these parameters along with the Maxwell model into OptiSlang, where we can quickly run these optimization studies. Ansys OptiSlang is a powerful tool for optimization and statistical analysis. AEDT integration and again Maxwell integration is available, and it is easy to implement. Variations can also be run in parallel for faster computations. OptiSlang generates meta files out of the FEA tool like Maxwell for optimization. So as an example here, we can see how we can use OptiSlang for a permanent magnet machine on the left, and some of the responses that OptiSlang can generate, such as the response surface of how the torque would change with the magnet coverage or the wall thickness, or different other parameters for the motor. So we can also generate a meta model of prognosis from OptiSlang. So in OptiSlang, as an example here, a detailed example is the Nissan Leaf optimization example. We can see that there are 5 design variables chosen. One of them is a slot parameter, BS0. Then we have magnet parameters like the magnet thickness, magnet width. And we can use these design variables, the 5 primary design variables, and define a range for variables in OptiSlang, and we can perform sensitivity analysis. OptiSlang can generate meta model of prognosis, which is basically a ROM, a reduced order model based on input variables and the output responses. So here in this slide, we can see the response surface of the torque ripple on the right bottom corner here, on how the torque ripple changes with the magnet thickness and magnet width. So this response surface is generated by OptiSlang. In a similar way, we can also generate a COP matrix that shows how each variable, each of these 5 primary design variables, affects the performance of the machine. So here we can see all the 5 variables and how the output parameters for the machine would change as we change these variables. In a similar way, we can also use OptiSlang with Ansys MotorCAD as well. And the design candidates from MotorCAD can be evaluated against full design specification. We can do a multi-physics and multi-objective optimization by combining MotorCAD with OptiSlang. And the multiple objectives for drive cycle can also be specified to optimize the efficiency, reduce the volume or footprint of the component, and reduce the cost of the component as well. And some of these optimization studies, as well as generating the response surfaces, would require the users to run hundreds of these variations. So depending on the number of variables that we are trying to optimize, the design space can explode into hundreds of variations, and the users may run into hardware limitations. And we can also use now AEDT or Maxwell in the cloud. So Maxwell is available in the cloud where there are multiple nodes available. So the users can run the variations faster, and there are multiple cores available, as well as sufficient memory, plenty of memory available for all these parallel solves. So Ansys is partnering with Microsoft Azure to create the secure cloud solution. Users can directly access Maxwell on cloud and be able to use high performance computing. As an example here, we can see how the solution time can be reduced by increasing the number of cores available to a given solution. So if this is the time savings for a single solve point, and when we run these optimization or parametric sweeps, this is scalable across hundreds of variations. So the user sees a real benefit in the speed up of the simulation by running Maxwell in the cloud.
So thank you, Pavni, for covering the part where we are showing how someone can optimize the electric machine design, not just electromagnetically, but even for thermal and structural performance. So far, we have just covered how electric machine design can be done at component level. And this being a conference of electric machine design and drives, In real world, both these things would work together. So how does someone model drives along with machines?
That's a very appropriate question, and we have the right audience here today to address that. You're right. So I may be designing the best motor in the world, but if in the end, this machine would be driven by a drive. It may have some mechanical loads interacting with it. So and we would want to see how the system level efficiency is, not just the electric machine efficiency. So we would want to account for switching losses in the inverter. How would the battery interact with this? How would any mechanical and dynamic loads change the system performance? So we can bring this all together in Twin Builder. And with this workflow, we are not only looking at the electric machine design, but we are also accounting for how each of these other components, like the battery, which is the power source, or how can we optimize the inverter, how can the cable parasitics interact with this electric machine operation. So we are accounting for all of these factors when we bring the whole system together. So component optimization, often when we optimize just the motor or just the inverter or just the battery, each component optimization in silos will not work in the real world. And this workflow with Twin Builder will optimize the system itself. And as an example, specifically for electric machines, there are several ways on how we can take an electric machine model into a system level. So one of the methods here is generating an equivalent circuit model using the DQ flux linkage model from Maxwell or MotorCAD. We can also export the electromagnetic losses and control models. We can take the efficiency map data from Maxwell and MotorCAD into Twin Builder. In a similar way, we can also export the thermal model from MotorCAD or the fixed resistance network into Twin Builder. We can also do a high fidelity FEA co-simulation where Twin Builder and Maxwell would run hand in hand with a handshake analysis. We can also do the electromagnetic loss control co-simulation with a functional markup unit. And MotorCAD can generate a FMU into Twin Builder to enable this kind of analysis. In a similar way, on the thermal side, we can do a thermal model co-simulation, and a functional markup unit from thermal is also supported in Twin Builder. So with all these different approaches, we have several solutions to account for the machine at a system level and do the full analysis with Maxwell, MotorCAD, and Twin Builder. So in this session today, we covered some of the key aspects for electric machine design. We talked about how the machine design can be done at different stages of a product life cycle, from the initial design to a more detailed multi-physics coupled analysis with finite element tools. And we also talked about optimization of the motor, and we covered how we can do the full system level simulation by accounting for the motor and the drive and any other components of the system, such as a battery source, mechanical loads, and calculate the full system level efficiency with Twin Builder. With that, I'm going to hand it over to you, Ronak. Thank you.
So thank you, Pavni. This was a great presentation where we covered everything that ANSYS had to offer for electric machine design. Ladies and gentlemen, thank you very much for attending this session today. If you want to reach out to ANSYS regarding any of the solutions that were covered today, please reach out to us here. This is the webpage for ANSYS Electric Motors. You'll find a lot of information here, application notes, upcoming webinars, even webinars on demand, and information on all the other multi-physics solutions that Pavni covered. And we look forward to get in touch with you. Thank you very much.